A learner's working memory has a limited capacity. That's our essential learning number one. Now, that's the first thing that can go wrong in your working memory, is we can exceed the working memory's capacity. Remember when we talked about the capacity of working memory from our information processing model, and we said it's about 7 plus or minus 2 chunks of working memory for adults. So that gives us a range of somewhere between 5 and 9. So as long as the learning task is at that level or less, we should be okay, right? So let's take it a common school learning task and let's count up the chunks and let's see if it might work in working memory. So I bet you'll recognize this one. Let's write it out. This is long division with a remainder. So let's just count up as the learner solves this how many chunks it will take. I mean, given that we may have 7 plus or minus 2 available. So 5 into 328, so step 1 would be to divide 5 into 328 and get 6, so that would be 1 chunk. 6 times 5 is 30. The second step in a division problem is to multiply, so that would be 2 chunks. Subtract, that would be 3 chunks. Bring down, that would be 4 chunks when you bring down the 8. Now we're going to divide again, 5 into 28, so we're up to 5 chunks. So let's multiply to get 25, so that would be 6 chunks. Subtract to get 3, so we're about up to 7 chunks of working memory for a novice, for a tourist, for someone who's been through this now only a couple of times. Does that make sense? And you might say, well, that works out okay. They have 7 chunks, right? Remember, 7 chunks are for an adult. At what age do we teach long division with a remainder? Not to adults. Typically what? 3rd graders? 4th graders? What about in your school district? Let's take a look at a chart. Here's a chart that shows the relationship between working memory capacity and age. Now, we said that an adult, and when we speak of an adult, we mean developmental age, 15 or higher. So if you're a 15-year-old or an adult or higher, you've got about 7 chunks of working memory. But what if you're a third or fourth grader? How old would you be? 9, 10 years old maybe? Let's take a look. If you're that age, come across, only about 5 chunks of working memory are available to you at that age. See how that could be a problem? 7 chunks needed, 5 available. You could overload the working memory. You could be a very capable, bright 3rd grader, and the first few times through, you could really have a problem with that, couldn't you? Let's take a look at another example. What about this one? Addition of complex numbers. This always gave me a headache. And why not? Look at this. I mean, it gives you a headache just to look at this stuff, doesn't it? Let's count up how many chunks of working memory it takes to successfully solve a problem of addition of complex numbers. First, you start out with complex numbers, right? But you can't stay there. You have to change the complex numbers each to proper fractions. So here's a few chunks right there, 1 and 2. And then you're not finished. You have to take those improper fractions and you have to add them. So then you have to find the common denominator. So there's at least chunk 3. And then we add them. That's chunk 4. And then we have 131/15. You'll never get it right if you leave that as an answer. So you have to take this improper fraction and change it back into a mixed number. So that's 5. So at least what? 5 chunks that it takes to successfully solve this problem. Now, the idea is this. In a learner's working memory, we have a limited capacity. So what happens when we have more chunks needed than what we have available? We have what is called a working memory overload. Working memory overload is a state of rapid forgetting induced by a learning task that exceeds the capacity of working memory. Anytime we exceed the capacity of working memory, it overloads. And what happens is all those chunks that we were working on, well, they decay. Let's take a look at our information processing model again one more time. Here's our model for working memory. Here's all the chunks that perhaps we're working on. Let's say perhaps that it's that long division problem, or let's say it's the division of mixed numbers. Let's say that you're a tourist in a new town and someone's giving you directions. As soon as the number of chunks that you can handle, as soon as the number of chunks that you are attempted to working on exceed your capacity, you have an overload. When overload occurs, the decay valve opens and everything that you're working on decays. Now that's an important point, because it's not just the last chunk that you were working on. It's not just that last math problem that you were attempting to complete, but everything seems to fall apart. In fact, if there really were a decay valve and an information processing model in the brain, whenever a learner encountered a working memory overload, I think perhaps maybe this is what it would look like. So do you ever feel like that happens to you during your day? The decay valve opens, and I know it happens to me several times a day. And here's the process. Whenever my working memory encounters more chunks than it can deal with, it overloads. It has a working memory overload, and that always opens up the decay valve. All the chunks that I'm working on are then gone. Rapid forgetting. Now that's what we don't want to happen. How can we prevent that from happening? How can we prevent the overload from occurring? You know, it would be nice if we could just give people more chunks. Here's 5 more for the day. It'll help you. But we can't do that. The secret then is to build the sophistication of the chunk. Since we can't change the number of chunks that people have, then we advance the sophistication of the chunk. Some of the studies on working memory have involved actually looking at the game of chess and chess masters, people who play chess successfully for a living. You know, it's really an amazing set of chunks that a chess master has. Let's say I'm a novice chess player. You know, I'm just okay with the game of chess, and let's say I'm playing a master of chess, and you could somehow look at the working memory of both of us during the game. Here's what you would see. We're both adults, right? So we both have, what, 7 chunks each? So maybe my first move or my first chunk would be that the pawn is in the front row. That's a sophisticated chunk, right? Now the master chess player would actually be thinking of maybe a 17 move chess strategy, where they would set up a position on the board where they can put me at a 2 or 3 move disadvantage, right? I'm thinking 1 move and they're thinking 17 moves. My second chunk of working memory may be that the knight has to move in an L shape. So I would do that. The chess master's second chunk is probably a 62 move stalling strategy, where they go all around the board and they're anticipating what they're going to do, and they go here and here and here and here. They've actually done research, and they've shown chessboards in the middle of the match to a chess master for only a few seconds, and you know what they can do? They can accurately remember the position of every piece on the board. Why? It's a pattern to them. They've been through it before. So the reason the chess master is so much better at chess than me isn't because they have more chunks than I do. It's because the chunks that they are using are larger, more sophisticated, maybe 10, 20, 100 times more information in one of their chunks as is in one of mine. So there's a key to communicating, to teaching, to working memory overload. Build sophistication of chunks. So going back to that division lesson, if we're teaching this or any concept, if we're learning something, if we can combine things, combine processes, and learn those combinations so that they actually become one chunk, freeing up more working memory to deal with the remainder, dealing with one problem to be more successful. That's called chunking.